Hi guys, thanks for tuning in. In this video, we're going to talk about limits and end behavior for multivariable functions. So we have a function f of xy equals 2 sine x plus 2 cosine y, and we want to ask, does this function have a maximizer, a minimizer, both, or neither? And so first, we should probably define what a maximizer is. So a maximizer is an ordered pair x naught, y naught, such that f of x naught, y naught is the global maximum value for f. Similarly, for a minimizer, ordered pair x naught, y naught, such that f of x naught, y naught is the global minimum value for f. So let's plot this function out and see what it looks like. So here it is. Here's f of xy plotted in the xyz in xyz space. And we can see that this function has a single global maximum of 4, but it achieves it many times. So when I say a single global maximum value of 4, I mean that the biggest this function is ever going to get is 4. Because when sine is equal to 1 and when cosine is equal to 1, we have 2 plus 2, which equals 4. So a single global maximum value, but there's many, many points at which we achieve that global maximum value. Similarly, for minimizers, there's a single global minimum value of -4 when sine is -1 and cosine is -1. Then this function has an f value, a z value of -4. You could see them down here. We could see that there's a single global minimum value of -4, but it's achieved infinitely many times. So if we try to formalize this, when we talk about the global maximum for f, the global maximum value for this function is 4. A single value. But it's going to achieve this global maximum value infinitely many times. So we could say that this function has infinitely many maximizers, infinitely many ordered pairs, x naught, y naught, such that this function is going to achieve a global maximum value. Same thing, similar idea for global minima. So we could see this right here. This is an ordered pair. When the sines are at pi over 2 plus any multiple of 2 pi, and when the cosines are at 0 plus any multiple of 2 pi, that's infinitely many ordered pairs that when we plug those in to f, we achieve this global maximum value of 4. Okay, same idea for global minima. So this function has a single global minimum value of -4. But there's infinitely many ordered pairs at which it achieves that global minimum value of -4. So that's this set right here. This function has infinitely many minimizers, infinitely many ordered pairs that when you plug one of those ordered pairs into f, we achieve this minimum value, global minimum value of -4. And those occur at basically 3 pi over 2 comma pi, but we can add any integer multiple of 2 pi into either of those slots in the ordered pair, and we're going to get another global, another minimizer, another point at which we achieve this global minimum. And we could see that happening here, infinitely many places at which we achieve that global minimum. All right, let's try another one. So here's another problem here, f of xy equals, I don't know, it looks like we have some sort of polynomial equation in the numerator, some sort of polynomial equation in the denominator, and we're trying to figure out, does this function have a global max, a global minimum, both, or neither? Plotting it is a good place to start. So when you look at this function in a plot, you might think, oh, it looks like it's going to be a global minimum, just based on what we see in this particular plot. But you need to be careful not to overgeneralize from a single plot, right? The plot suggests we have a global min, but maybe looking at one little plot is not good for trying to assess global behavior for a function. So we could try to use limits, we could try to use better graphing techniques, because my concern here is if we zoom out, okay, well, now we can kind of see, no, this is not a global minimum, because when we look at more of the picture, we can see that it looks like we go to positive infinity in some directions, negative infinity in other directions. I think what looked to me like a global minimum in one camera angle and one plot is actually just a local minimum. So when we're looking for global extremes, a small little local plot is probably not the best way to determine the values for global extremes or the existence of global extremes. We need to look at the behavior of our function, yes, near the origin, We need to look at places where the function can blow up. Basically, if you're dividing by 0 or something, or close to dividing by 0, the function can have some crazy behavior. But the big one is we also have to look at the end behavior of the function. What happens when we get away from the origin? And if you analyze kind of these three things, you could do a pretty good job of figuring out if your function has a global max, a global min, both, or neither. And I like starting with end behavior, because this is something that you guys studied a lot in your Calc BC class, and you spent a lot of time calculating limits last year. Limits are a little more complicated in this case. So for this particular problem, I can say, is there a hiking trail that I can hike on that as I go on that hiking trail, f of xy tends to, say, infinity? If it does, f of xy doesn't have a global max because there's a way to make our function go to infinity. And then if there's another hiking trail where f of xy tends to negative infinity, again, our function does not have a global minimum. And so if we could produce that behavior in our function f, we can definitively say that our function does not have a global max and does not have a global min. So let me rerun this code and just kind of imagine all these possible hiking trails. If I can find just one hiking trail that the f of xy value goes to positive infinity, maybe this one, then I could definitively say this function does not have a global maximum because I'm able to drive f of xy to infinity. And if I could find a different hiking trail that the f of xy value goes to negative infinity, something like this, then again I can definitively say this function does not have a global minimum. Now, you can see that happening in this picture. This is a function that has a local minimum, but that local minimum is not a global minimum because I can send my function, presumably, to negative infinity. But I'm going to try to produce some more rigorous results to prove that this does go to negative infinity. All right, so let's try out some ideas here. So let me just make up a really simple hiking trail. And just to keep things simple, I'm going to set x to a constant of 0. So I'm going to turn this function into something that looks more like something you would have looked at in Calc BC. So let's set x equal to 0. So I have f of 0 comma y. This would represent a single hiking trail where x is 0, but y is allowed to vary. Well, in that case, this function simplifies to y cubed minus 6 over y squared plus 1. And if you saw this in Calc BC last year, you would say, I know how to take the limit as y goes to infinity on this function. It goes to infinity. Well, that's definitive mathematical algebraic proof that this function tends to positive infinity. Therefore, it does not have a global maximum. We could look at a plot that kind of illustrates this. Imagine walking on this red hiking trail and you're going further and further and further. And you could see that as you continue on this hiking trail, your z value is going to tend to positive infinity. This function has no global maximum. We could repeat this logic for minima. So in this case, it probably makes sense to just do the same thing again. Plug in x equals 0 and allow y to vary. And again, that reduces to just a curve, a red curve on our surface, a hiking trail on our surface, that if I walk that hiking trail as y tends to negative infinity, this ratio of polynomials goes to negative infinity. Again, definitive proof that this function does not have a global minimum. This local-looking minimum right here is just local. It's not global because there is a hiking trail I can walk to go to negative infinity. So anyway, long story short, if you can produce a limit that takes your function to infinity or negative infinity, that's a good way of proving that f of xy does not have a global maximum or a global minimum. However, just because you can use a single hiking trail to prove that a function does not have a global maximum or does not have a global minimum, this technique is not very useful for proving that a function does have a global maximum or does have a global minimum. We have to be careful. So we have to, not overgeneralize this technique here. So, for example, does f of xy equals xy have a global minimum? What about a global maximum? If we're not careful, we're going to produce some not very useful mathematics here. So I'm going to evaluate my function at f of x comma 0. Okay, so f of x comma 0 equals 0. So the limit as x goes to infinity of f of x 0 equals 0. And so if you're not careful, you'll say, oh, that means that f of xy has a global minimum at 0, because I followed a single hiking trail and it went to 0. Well, okay, a single hiking trail doesn't prove that you do have a global minimum. It just proves that there's one way that you can walk to send this function to 0. But that's not the global minimum, it's not the global maximum, it's just a single hiking trail. So the technique with limits like that is really only useful if you're trying to prove that a function doesn't have a max or doesn't have a min. Watch this. If I pick a different hiking trail, I can send this function to f of xy goes to infinity. And if I pick a different hiking trail here, I could send this function to negative infinity. So a single hiking trail going to 0 doesn't really say much of anything. We have to be careful. Basically, we have hiking trails that do all sorts of interesting things. A single hiking trail doesn't prove that you do have a max or a min. It's just good for showing that we don't have a max or a min. Watch. I'm going to take the same function. I'm going to consider the case where y equals x. So f of x equals x squared. Oh, well, if I send x to infinity, this function goes to infinity. Or if I consider y equals negative x, if I evaluate f at y equals negative x, I get negative x squared. I can send that function to negative infinity. These hiking trails prove that f of xy does not have a global maximum, because I can send it to infinity, and does not have a global minimum, because I can send it to negative infinity. So a single hiking trail doesn't prove that we do have a local max or global max or min, but it is useful for showing that we, if you could send it to infinity or negative infinity, it's useful for showing that we don't have a global max or a global min. Right, let's try one more. So here's another function. Does it have a global maximum, a global minimum, both or neither? Again, a single hiking trail is not going to help us. So let's take a look at why that's the case. So watch, there's infinitely many hiking trails we can take. And each of those hiking trails has a different limiting value for what f of xy tends to. We would almost have to consider every single one of these hiking trails at once to prove, like this point up here, this might be the global maximum. But I kind of have to look at every single hiking trail to know that one of these hiking trails doesn't make it higher than what looks like might be the global maximum here. Like maybe one of these hiking trails eventually starts to go uphill again and achieve a value that's higher than this local maximum point here. And I'd have to think about 360 degrees of hiking trails to prove that if I was going to use limits. So let's zoom out here and see if we get a better idea. Oh, this is the same picture. Look at this. In 360 degrees of hiking trails here, it looks like these all tend to 0 as we get really far from the origin. We want to try to leverage that observation into a proof. If we can prove that every single hiking trail in every single possible direction tends to a z-value of 0, then we could use that to prove that this value that is greater than 0 is our global maximum. Same idea for the global minimum. I think that I have one global max, one global minimum, but a single hiking trail is not going to prove that. I need some better algebra to prove that. So that's where tutorial T4 turns into a good set of arguments, and we're going to use that. So we have f of xy equals this equation. And what we say is when absolute value of x and or absolute value of y are large, as we move away from the origin, then the dominant terms in the denominator make f of xy really, really close to 0. Basically, as we move away from the origin, f of xy tends to 0. Now, the other thing we notice is that we can make this function positive, and we can make this function negative. So what we have is a surface that away from the origin tends to 0, but near the origin can be both positive and negative. And that is definitive proof for us that this surface has a biggest crest and a deepest dip, a global maximum and a global minimum. Because near the origin, we have a function that takes on positive values some places, negative values other places, but as you move away from the origin, it gets very, very close to 0. And so we have a biggest crest, a global max, and a deepest dip, a global minimum. So this sort of argument here is very, very powerful. So understanding tutorial T4 allows us to consider all possible hiking trails as we move away from the origin, and then we can use that to come up with definitive proof. That argument is as powerful as taking essentially an infinite number of limits. What happens to every single hiking trail as we walk away from the origin? And so anyway, hopefully this video helps you make a little bit more sense out of the arguments in tutorial T4 because it makes them very visual. And as you read tutorial part 4, try to adapt those arguments for your own purposes on your own triad problems. All right, guys, thanks again for tuning in. I hope this video was helpful.